Hi, good morning, everyone. I'm Fujii, and today I'd like to talk about 3D image acquisition and processing. I delivered a handout, but its content is too much. Today's talk is very short, just 40 minutes. Okay. So first, I'd like to start with this figure. Have you heard of 3D communication system? Maybe this is the 3D camera. That this has two cameras, okay, and this is 3D display. Have you ever seen 3D displays? Maybe you can go to a cinema, 3D cinema, or you can watch some 3D contents with DVD contents or something. And this is a traditional 3D capturing and transmission and the display system. And today's talk, this is the items of today's talk. In today's talk, I'd like to draw your attention about what is 3D and what is 3D processing, 3D image processing. Okay. So first, the question is this: what is a three-dimensional image? Do you have an idea? Okay. So let's start with this. Okay. So this is a figure of a future 3D imaging system or communication system. This is from Ministry of maybe Communication, Ministry of Communication. They published this figure. That you can watch 3D image in your home, like this. That you can watch soccer game, the football game, on the living room at your home. So this is kind of this 3D system image. Maybe in Japan or in the world wide, I'm not sure, but around 2010, it was called the first year of 3D TV. At that time, many 3D displays or 3D related products was in the market. Okay, 2010. So, okay, this is the first question. What is 3D image? As I said, there was a buzzword in 2010, around 2010, the 3D image. But at that time, 3D image was like this. Okay, you have left image and right image, and with your glasses, you can perceive 3D impression. But what is dimension? What is the dimensionality? This is called the 2D image. The 2D means this has two-dimensional or two axes. Okay, so X and Y. This is two-dimension. So this 3D should have three axes, X, Y, and Z. But this has only two 2D image. Okay, so can you call it 3D image? That is a question about this. It's a number of dimension 3. For example, 3D computer graphics, like this, it is called 3D, but you have only 2D display. Your display is not 3D. So what is 3D? This is a question. And you have to remember these human factors. I'll describe this about it. What is the human factors for 3D perception? So these are the 3D perception factors. This is called cues of 3D perception. The first one is the size. This is a big objects, and if the object is far away, it should be very small. This is size. This is the first factor or first cue. And the second is perspective. This is picture or drawing based on perspective projection. This is perspective. And overlap, like this. And the next is shadow. Do you feel some convex or concave shape here? Okay. This is based on the shadow. Okay. Or texture, you can feel 3D. But this is useful only on 2D image. Even if the dimension is 2, you can perceive 3D perception. This is just a 2-dimensional image. So this line is very important. Please remember these words, okay? The disparity and convergence, accommodation, and motion parallax. These four factors are very important for 3D perception. This is not realized on 2D display. We need special 3D display. Okay, these four. Please write down this for your report. Okay, disparity, convergence, accommodation, and the motion parallax. The disparity is the difference between the left eye image and right eye image. This is called disparity. Okay, you can see the different aspects of the objects. Okay, from left direction, from right direction, you see the same object but slightly different image. Okay, this is called a disparity. The next is convergence. Convergence means this is the optical axis of eyeball, and the eyeball optical axis converges at this point. Okay, so if you see near eye object, convergence point comes very near, and if you see the object at infinite distance, the optical axis is made in parallel. Okay, so this is called convergence. And the next is accommodation. Accommodation is the focal length of eye lens. Okay, accommodation. This is motion parallax. If you move around the object, you see the different aspects of the object. This is called motion parallax. Okay, this is the most important point. 3D displays utilize these factors, not these factors, but these factors, these four factors. Okay, so there are many kinds of 3D displays like this, and the oldest one is like this. In 1838, Wheatstone invented this kind of 3D display. The left eye sees left picture, and the right eye sees right picture. Okay. This is the oldest one. This is almost 100 years ago, 1903. Ives invented parallax stereogram. So right eye sees this part of image, and also this part of image, this like this, and left eye sees this part of the image, this part of it. So using this principle, we can separate right image and left image. Okay, so you can see 3D image without glasses. Okay, this is 1903. This is also very old one, 1908. Lippmann invented integral photography. So he used lens. At that time, it was very old, 100 years ago. So there was no technology to fabricate lens. So he didn't realize this one, just a concept. There are many lenses, very small lenses. For example, about 200 or 400 number of lenses. and each lens acts as a camera. Okay, this object is captured like this here. This object is recorded here. So this is equivalent to very large number of cameras. This is one. This is capturing, and this is display. At that time, there was no digital image, just a photograph. And this is film. And the film is set here and illuminated from right side. So you can see 3D real image here. This is very old but very basic principle of integral photography. Okay, these two are very old but very basic principle. Please remember these two: parallax stereogram and integral photography. In fact, there are many kinds of 3D displays now, but almost all the 3D displays are based on these two principles: integral photography, lens-less display, and this type of parallax barrier type display. Have you ever heard of the Nintendo 3DS? Nintendo 3DS game machine is based on this principle. So these two principles are very important. Okay, I'll introduce another type of stereos. This is based on binocular stereo, show two images from different viewpoints. Maybe you've seen this kind of red and blue image. And this integrated image is separately viewed using 3D glasses, red and blue glasses. This is called anaglyph images. This is very common. Okay? And another type is polarized glasses or shutter glasses. These principles are used in 3D cinema these days. Okay? At the entrance of the cinema, you can borrow the glasses. This is based on polarized or shutter glasses. Okay. Or lenticular is basically similar to integral photography, as I described, and the parallax barrier is another very important basic principle. Lenticular is a simplified version of integral photography. Okay, this is a lenticular lens. In the case of integral photography, there are many lenses, the high number of lenses. On the other side, this is the not full circular type lens, but this cylindrical type lens. Okay, this is a difference. It's lenticular type. And another is a parallax barrier and multi-view stereo, and another type of display. Okay, the other type of 3D display is holography. Holography is a technique that enables a light field, which is generally the product of light source scattered off objects, to be recorded and later reconstructed when the original light field is no longer present due to the absence of the original object. Yes, maybe you've seen holography. Or holography is the name of a technique. Hologram is a picture based on holography. Okay. So this is called the ultimate 3D display because this holography can fulfill all the requirements for 3D displays. I pointed out four factors. That this can fulfill all the four factors. But the problem is we need to record fringe pattern using very high resolution material that this is realized by chemical substances. So it's very difficult to replace this fringe pattern with digital technology. This is a very difficult one. So it is very difficult to realize holographic video. But this is very interesting research. Around 1990, MIT Professor Benton invented this kind of holo video. The point of this research is he used AOD or AOM, acoustic optic modulator, light modulator, or acoustic optic device, the AOM or AOD we call it. Okay, so he used this as a display of fringe pattern, very high resolution fringe pattern. So this can display a very small fringe pattern, for example, less than 1 micrometer. Okay, so it's very small. For example, LCD display we have that is available now have about 10 micrometer. So one order less than today's technology. Okay, this is very important and interesting work. But the drawback of this AOD or AOM is fringe pattern is not still. It moves with a speed of about 100 meters per second, very fast. So to compensate to this movement, he developed this kind of optical system. Okay, so in other words, this optical system chases the floating image. This is very analogical explanation, but it's something like this. Okay, so at that time, to calculate this hologram pattern was very huge. It requires very huge computation. So when I visited Massachusetts Institute of Technology around 1991 or 1992, I was shown the demo. If I switched the like joystick, when I control the joystick, the image moves. But behind that, there was a building. The building is filled with the supercomputers, and the fringe pattern is calculated at that building. That's very impressive research at the time. And now, this is a photograph of integral photography, as I explained, 1908 integral photography. But NHK, Japan Broadcasting Institute, developed this kind of integral photography. The point of this technique is they invented a new lens, not ordinary lens, but it's called green lens. It is a fiber lens. So they aligned many fibers like lens. So this is the key technology to realize this IP, digital capturing as digital transmission and digital display. So they developed around 1997. Okay. So they are continuing this research up to now. This is a figure from NHK. So they are developing this IP-based display. The image is like this. This is the image from left viewpoint. This is image from right viewpoint, from upper viewpoint and from lower viewpoint. Then you can see 3D image like this. Okay. And I'll skip this. Okay, This is ray reproducing cylindrical display developed by Yendo sensei. He is now Nagaoka Institute of Technology. He was assistant professor at Nagoya University about 10 years ago. He developed this kind of cylindrical 3D display. Okay. It's like this. So I can show you some videos. Okay, this is a video. This is cylindrical type 3D display, and you can see as if a lady is in the cylinder. So this display can emit light rays to 360 degrees, and this data is consists of 360 images, still images. Okay, so this display can show 360 images simultaneously, 1 degree per 1 image per 1 degree, 360 displays. Okay, this is a very interesting one. And back to the slide. These are displays from NICT, okay, National Institute. This is a cube-based 3D display, but principle is just the same as integral photography. This has 6 phases of IP display, integral photography displays. And this is called F-Vision. This is tabletop display. Okay. This is a very interesting one, 200-inch, very large size, 300-inch 3D display. But the principle is 200 image is projected from behind, and in between there is a screen, and the screen acts as a lenticular seat, lenticular lens, and you can see 200 views, 200 images simultaneously. This is a very big project. It was displayed on the north of Osaka station, Umekita Chiku. But now it's disappeared, unfortunately, about 3 years ago or 4 years ago. Okay, this is the introduction of 3-dimensional image. And the second topic is the theoretical one. That I'd like to introduce this theory very short. Okay, this is a very old slides when I was a PhD student, 1992. So at that time, people said that 3D image will be very popular in a few years when I was a student. So my professor and my supervisor said to think about the 3D communication or transmission method. So at that time, even at that time, there was many kinds of 3D images. I explained the multi-camera array or computer-generated, the hologram. There were many types of 3D images. And the point was the input and the output is 1-to-1 corresponding. Okay? So if you capture a scene using multiple cameras, that data is transmitted and displayed on a multi-view display. if the input was computer generated, the output was spatial imaging. And if input was hologram, the output was hologram. This was one-to-one corresponding. So my supervisor told me to think about this kind of transmission system. Various kinds of 3D display data is converted to a common data format, and it is compressed and transmitted to the receiver. And at the receiver side, this converted common data is again reconstructed or converted to original form. Okay, this is the concept of common data. My supervisor said that to think about this, but what should be this common data format? So I considered about this. I researched on this topic for 3 years, and then invented this kind of integral 3D communication system. Many kinds of 3D images converted to common data format. So what can be a common data format? This is a question at that time. So ray space representation was derived from that notion. Okay, I'll explain briefly this ray space representation. This is object, apple here, and light is coming from light source and reflected on the surface of the object and come to our eyes. Okay, so we observe this scene, but our eyes just detect light rays, not the object itself, light rays. So if we can describe all the light rays in the scene, we can reconstruct or we can represent the scene. That was a basic principle. So parameterization is not so important, but this is one example of parameterization. Okay, we have X, Y, Z 3 axis here. The origin is here. And first we introduce the intersection coordinate X and Y here. And outgoing rays, the direction, the theta and phi. So if we define the f, function f of x, y, theta, phi, then we can describe this scene. This is a basic concept of ray space. Okay, so think about that. As I said, what is 3D-dimensional image? Now, 3D-dimensional image is just 2D images. But in reality, 3D images like this. 3D image is not 3-dimensional, 4-dimensional image. Okay, this is a very important takeaway message of today. Okay, 3D-dimensional image is not 2D images. 3D-dimensional image is 4-dimensional function space. Okay, this is a very important notion. Okay, let's think about this example. So we capture this scene using many cameras, for example. And this is simplified version of ray space. Phi is omitted, just x, y, and u. U means a tangent theta. Okay, so the camera 3, for example, captured this scene. So what is the image of captured image by camera 3? So according to the definition of ray space, this camera image corresponds to an image, section image of ray space here. So camera image 1 corresponds to the section image here, number 1. Okay, so if we capture this scene with many cameras, that means we collect all the section images. of ray space. This is a relationship between real space and ray space. Okay. So once we got all the ray space images, we can generate arbitrary viewpoint image. If we cut this volume, 3D volume, by here, like for example, we can get this section image like this. If we cut the volume here, we can get this cross-section image. So this ray space includes all the viewpoint images. And if we'd like to generate arbitrary viewpoint, what we have to do is just cut this volume, ray space volume, and extract the section image. This is generation process, very simple. Okay, this is a very important relationship between real space and ray space. The ray space is like this. This image, it has line structure. I skip this, okay. We can think of another coordinate system. This is spherical, called a spherical ray space. The definition of the spherical ray space is like this. Just the difference is just definition of this plane. The plane is defined by theta and phi, and the position is no more x and y, but x and eta. The relation between the real space and ray space is written like this. Okay, x equal minus r sine theta minus alpha. This is example of a ray space here, 360 type spherical ray space. It's like this. And okay, this is a orthogonal ray space as described before, and this is spherical ray space. Okay, and I'll show you some of this. Okay, so this is the paper on 2002 called the free viewpoint TV system based on ray space representation. So this is a new type of 3D transmission system. Scene is captured by some means. For example, many cameras. And some interpolation or some processing is done, and we get ray space. This is in-between data format, common data format. And ray space coding, compression, processing is done at this stage. And then at the receiver, just extract the cross-section of the ray space. Okay? Then we can see arbitrary viewpoint image, free viewpoint images. Okay? This is called the free viewpoint TV system. Okay, last 5 minutes. So just we'll today focus on this part, acquisition part. How can we get ray space here? So there are roughly 3 types of capturing or acquiring system of ray space. Number 1 is multi-camera system. We developed 100 camera system. The second is space division multiplexing. Integral photography is one of them. And the number 3, time division multiplexing, optical system plus high-speed camera. The first one is multi-camera system. This is a very simple multi-camera system. It consists of 8 cameras or 4x4, 16 cameras, multi-camera system. And we developed in our laboratory 16 camera system. This is a camera. This is old one, analog one, the very small, like this size. And each camera is connected to a capturing board in a PC. So at that time, there was some trends worldwide to develop a very high number of camera systems. For example, this is a very famous one. Stanford University developed about 128 cameras or something. So, but they didn't say multi-camera system. High performance imaging using large camera array, they say so. Or Carnegie Mellon University developed this kind of self-configurable camera array 2004. And we, Nagoya University, developed 100 camera system. So like this. Yes, this system was in the 6th floor of West Building of IB. Now, leading studio and the leading room is there. This 100 camera was developed at that place. And specification was very, at that time, very advanced. Resolution is 3092 by 1040. At that time, it was very high number. The raw data was recorded, and the synchronization of each camera was less than 1 microsecond, very high accuracy of synchronization. The camera is like this, and we aligned the camera in 1D line. The distance between cameras was 5 centimeters. So the 100 cameras, totally 5 meter baseline. Or we arranged the 100 cameras in 1D arc. The radius was 5 meter convergent type, or 2D camera array. 20 cameras by 5 rows, 100 camera system. Okay. Then we captured many scenes at the studios. Okay. And yes, this was captured on the 6th floor, the leading room at that time. Okay. This scene was captured. And we went to TV studio and captured many scenes like this. Okay, I'll show you, finally I'll show you some videos. You may have seen cinema, Matrix. This video was created before Matrix movie. Yes, this kind of bullet time scene using 100 camera system. Okay. And at that time, this is a musical instrument, and at that time, many microphone was set also. The Professor Takeda Sensei arranged many microphones. We set 100 camera system. Yes. And this is done. Sorry. Okay, I'll show you this aquarium scene. We captured this using 16 cameras. 16 cameras. We switched the camera. Okay, this is the input of capture scene, input of the system. And output was like this. This is processed one. The 16 camera input was processed and interpolated and created ray space. And we just cut the ray space and extract the free viewpoint images. Then we can move forward and go into the aquarium. Okay. This is a demo of free viewpoint images. Okay, now it's almost the time. So I started with this figure. 3D camera has 2 cameras. And the 3D display, we need the glasses. This is the first starting point. But in reality, this intermediate data is ray space, 4D function, 4-dimensional function. So there are many kinds of capturing devices, and we capture 4D function data and then transmit it 4D data and then display 4D data. This is takeaway message of today's talk. And this is IEEE Signal Processing Magazine, November 2007. So Much View Image 3D TV. He is watching ray space, the 4D scene. Okay. Thank you for your attention. Yes.